everyone, and welcome to our LIM Live program on KUTV. Today we are looking at mathematics revision for Form 4s, as we encourage you to keep revising from home during this time. Now, today we are going to look at the first topic in Form 4 we call matrices and transformation. But before we get into the details of matrices and transformation, I will remind you what we looked at in our previous lesson under matrices, which is going to form the foundation of this topic. And that is why matrices is taught in Form 3 to give you the foundation of what will happen in Form 4 topic 1. And so when we're looking at matrices, it is important to understand the main things that we discussed last time. What is a matrix? How do you get the determinant of a 2 by 2 matrix? How do you get the inverse of a 2 by 2 matrix? And then how do you solve pairs of simultaneous linear equations using matrices? Then we're also going to review something we learned in Form 2. In Form 2, topic number 6, that is reflection. Topic number 7, that is rotation. And topic number 8, that is enlargement. And then we shall go to topic number 20, which is about vectors, which now gives us another transformation to discuss in our lesson today. So in short, our lesson on matrices and transformation, being a revision lesson, is going to go through the concepts taught in Form 2 and the concepts taught in Form 3. We bring them together and we make them more of essence when looking at the topic matrices and transformation. So back to where we want to start from. The first thing that I want us to be able to review on is the elements. And these elements are arranged in what we call rows and columns. And we said when we talk of rows, then we refer to what we call the horizontal arrangement of elements. This is the horizontal arrangement of elements. And then we again said when we talk of columns, then we refer to what we call the vertical arrangement of elements. So elements or matrices have elements arranged in rows and columns. And then once we've been able to understand that in Form 3, we looked at various items like the inverse of a 2 by 2 matrix, the determinant of a 2 by 2 matrix was very important. And to say determinant, you simply take elements in the leading diagonal, that is A, D, minus the products of elements in the other diagonal, B, C. Then again, we reviewed what we call the inverse. And I say that in the inverse of a 2 by 2 matrix, you interchange the elements. Like in this case, we have A and D. So they shift the position. Where you have A, you put D. And where you have D, you put A. So you end up with a matrix D, A. Then for B and C, they change the sign. So in this case, we have B. We now obtain negative B. Then we have negative C. Then once we have this matrix, we multiply by what we call the reciprocal of the determinant. That is 1 AD minus BC. That is how we get the inverse of a 2 by 2 matrix. And finally, on that topic, what is important for us to note is what we call the solution of a matrix of simultaneous linear equations. Solutions of simultaneous linear equations. Linear equations using matrices. And we say that in this part, what we need to understand is the procedure that we adopt in solutions of simultaneous linear equations using matrices. And one of the procedure that we have to be very cautious about is for us to be able to obtain what we call the matrix equation. We obtain the matrix equation. And the matrix equation is obtained from the given equation. For example, if you are talking about 2x plus 5y is equals to 10 and x minus 2y is equals to 7, then these equations will give us what we call the matrix equation. And this is how it will happen. We take the coefficient of x for each case. So we have 2. The coefficient of x in the second equation is 1. Then the coefficient of y is 5. The coefficient of y in the second equation is negative 2. And this being elements from x and y to give us a matrix, an element that is 10 and 7. This is what we call the matrix equation. So the first thing is always obtain the matrix equation. And then step number 2, or procedure number 2, you now obtain the inverse. You obtain the inverse of the matrix, that is the 2 by 2 matrix. And in this case, this is the 2 by 2 matrix in our example. So we shall get the inverse of that matrix. And we say the inverse, you simply get the first, you get the determinant, which is the elements in the leading diagonal, that is 2 times negative 2, then we less 5 times 1. So this gives us negative 4 less 5, and that gives us negative 9. So when you come now to getting the inverse, you simply change the elements. Like we have in this case 2 and negative 2. We reverse those elements, so we have negative 2 taking the position for 2, and positive 2 takes the position for negative 2. Then change the signs of the elements in the other diagonal, so you have negative 5 and negative 1. Then now when you have this one, you multiply by 1 over negative 9. So this is what we call the inverse of the matrix. And lastly, we mentioned something we call you pre-multiply. And that is what we need to understand in our topic today, pre-multiplication of, in this case, of the inverse by the matrix equation. So you take the matrix equation and you pre-multiply it by the inverse of the matrix. Those are the main parts that we need to borrow knowledge from before we look at our topic today. So the topic that we are discussing is matrices and transformation. Now, the second part of it is transformation. So where are the transformations covered? Transformations are covered in Form 2. In Form 2, we have 4 transformations. That is reflection, which is covered in topic 6, rotation covered in topic 7, enlargement covered in topic 8, and then we have translation, which is covered in topic 20. So after looking at the first 4 transformations that are covered in Form 2, Form 4 only gives us 2 additional transformations now to make them 6. And so we are going to look at the 4 transformations in Form 2 and then add 2 new, which is now the shear, and then we shall discuss the stretch. It moves an object from one position to another, from one position to another within the plane. That is what is a transformation. And so in a plane, the figures or those objects within the plane changes position. So the issues here is about the simply change in position. Change in a position. So an object can only undergo transformation if we can be able to see there is some change in the position on the particular plane that we've been given. And we have different transformations, as I've mentioned, and these transformations include, for those who have forgotten their Form 2 work, transformations number 1, we have what we call reflection, and then number 2, we'll discuss rotation. Number 3, we'll discuss enlargement, and number 4, we'll discuss translation. And as I've said, these first 4 are covered in Form 2. So Form 4 then is going to add us something new, that is what we call the shear, and then number 6, we discuss what we call a stretch. So these are the transformations that are covered in this topic. And the only difference and the unique thing in a way we are going to carry out this transformation from the previous way we dealt with it in Form 2 is that we are going to apply a matrix. And this matrix is going to be called a matrix of transformation. And that is where the name matrices and transformation come from. Because we are going to have an object changing into an image or changing the position to form an image after we've applied a matrix. And so the applied matrix then here becomes what we call a matrix of transformation. And that is why we have the topic matrices and transformation, bringing transformation and matrices together to form the image. So let's first of all understand, what do we need to look at in a reflection? What do we need to look at in a rotation? And so how do we define the two transformation? Now, there is what we call isometric mappings, where you get the image and the object have the same size and shape. In this case, if you find that kind of a case where a transformation maps an object from a certain position to another position and they maintain the same size as the object, then in that case we shall talk about isometrism. And so we are going to see different matrices, different transformations that are isometric in nature. And so we call them isometric mappings. But more importantly, what you need to understand is that this topic requires your understanding to know how do you obtain an object given the image and the matrix of transformation, or how do you obtain now the image given an object and a matrix, or number 3, how do you obtain the matrix of transformation when you're given the object and the image? Those are the 3 aspects that we must analyze in our lesson today and then be able to practice on them as time goes by. So let's first look at what this entail. When looking at a reflection, in a reflection, I've mentioned that the image and the object size are the same, and the distance is also the same. But when you're describing a reflection, how do you describe a reflection in mathematics? A reflection is described. This one is described by simply stating the equation of the mirror line. The equation of the mirror line. And the equation of the mirror line, given it's a straight line equation, is in the form y is equals to mx plus c. So whenever you work out an equation and you want to confirm that it is a reflection that has taken place, then you must tell us what is the mirror line equation in the form y is equals to mx plus c. If we have this kind of a scenario, if we have this kind of a case, when you have the object, we have different kinds of equation. We have the equation y is equals to 0. This is the x-axis. We have x is equals to 0, the y-axis. We have the common line y is equals to x, which has a positive gradient of 1. Y is equals to negative x, which has a negative slope of negative 1. These are common lines that we need to know when we are working out reflection. Then plus a general equation now, y is equals to mx plus c, that we shall also be analyzing in our lesson. Number 2, how do you describe rotation? How do you confirm to someone that rotation has taken place? Now, for a rotation to take place, then you must have what we call the center of rotation and the angle of rotation. The reason is, when discussing a rotation, it's simply a transformation that moves a point through a given angle about a fixed point. You move an object through a given angle at a fixed point. That is what we call a rotation. And so when you're describing, we say this one is described by stating, we state 2 things. Number 1, we state the angle of rotation, and this is given in degrees. And remember, it can be a positive angle or a negative angle. So again, back to Form 2. When do you talk of a negative angle of rotation, and when do you talk of a positive angle of rotation? A negative angle of rotation happens when rotation takes place in a clockwise direction. When it is positive, we take it in anti-clockwise direction. So that is the distinction between the negative angle and the positive angle. And then get to know the common turns. We have what we call the positive quarter turn, negative quarter turn, half turn, and so on. That will help you when we will be getting into questions that we will be revising on rotation. Then number 2, you have what we call the center of rotation. And when we talk of the center of rotation, it is a point AB, or in terms that is XY. It could be the origin, 0, 0, or any other point within the Cartesian plane. That is where we will have the center or rotation taking place. Number 3, we are going to discuss enlargement. So if you meet a transformation that has enlargement in nature, then this one, we simply magnify the object. It happens where there is magnification of an object, meaning the size changes. Now we can either have a negative magnification or a positive, and it can either be either a whole number or a fraction. So we can have either of the two, but that still remains to be an enlargement. So in an enlargement, this one now is described. Enlargement is described by stating two things. You state, number 1, you state the center of enlargement, the center of enlargement. And number 2, you state the scale factor of enlargement. Scale factor of enlargement. So those are the two things that we shall be looking at in an enlargement. Do we have the center, and then do we have the scale factor? And the scale factor can be a negative number, it can be a positive number, it can be a fraction, it can be a whole number, depending with the situation that you've been given in the question. And then number 4, we have what we call the translation. A translation is a part of transformation that is captured from vectors 1 in Form 2, and where we move an object along a certain number of units on the x-axis and a certain number of units along the y-axis. So it is usually given by a translation vector t. And in this case, then we describe the translation. This one is described by simply stating the translation vector. The translation vector t. Translation vector t. And this translation vector t, x, y. That is how we get to translations. You will realize that in this case, the first 4 transformations that we have, and most that is commonly, that is translation, reflection, and rotation, they are what we call the isometric mappings. Isometric mappings here means that the size of the image and the object are usually equal. Only in enlargement where things changes, because you may find an object being larger than the image, or the reverse happening when you are carrying out the transformation. And so again now, we are going to mention something to do with the shear and the stretch. So how do you describe a stretch, and how do you describe a shear? Now, what is important in a shear is for you to be able to understand what we call the invariant line. And when we talk about the invariant line, it's simply the line on which the points remains the same. The line that does not, the points on the invariant line do not change. They remain to be the same. So you give us the invariant line and give us at least one point and its image that is not on the invariant line. Because not all the points will be on the invariant line. Some of them will be on a different, will be out away from the invariant line, and they have the images again away from the invariant line. So state the invariant line and give us the point and its image that is not on the invariant line. Then for a stretch, we look at the scale factor. We look at the scale factor and then the invariant line. And that is why now, when you come to the connections of these two, you'll find for a stretch, we usually have relation to the enlargement. This is not the same as enlargement, but the connection is that it is based on the part of the scale factor, that there has to be a certain scale factor that is applied for you to be able to obtain an enlargement. And in this case, you find in a stretch, you are like pulling one of the sides of the object. You pull one of the sides of the object. Like, for example, if this is what we are having, this is what we have as the object P, Q, R, and S, then I can be able to obtain the image and then pull this side. I pull this side. So that now I have new R prime and Q prime. So I retain P prime and S prime at the same point. I've simply pulled that particular part. That is what we call a stretch. Comparing this one with a shear, in a shear, we have, if this is our triangle, let's use a case for a triangle. This is a triangle. Then I turn this triangle and obtain something of this sort. Then if this is A, B, C, then I turn this to be C prime, and B prime remains the same point, A prime remains the same point. So this line on which A and B is lying on is what we are calling the invariant line. Why? Because the points on this line do not change. And so it is called the invariant line. Again, in a shear, if you look at in a stretch in this side, you find that these points are not changing. So they remain to be what you call the invariant line. And that's why you're saying for a stretch and a shear, it is very important to know what is the invariant line. The line on which the points do not change on either case that we'll be applying on. But more importantly, be able to tell us which point, like in this case C and C prime, are away from the invariant line, and therefore they can be able to be given as an example of points that are away from the invariant line. So up to this stage, students, we've looked at the whole thing that we will be covering in this topic, the matrices, and then number 2, transformation. So now we want to get into the details of what each one of them entails, but we'll do them in form of questions so that we can be able to bring out the 3 aspects. And I've said the 3 aspects that we must start with is 1, how do you obtain the object, the image, given the object under a matrix of transformation? And number 2, how do you obtain the object given the matrix and the image? And number 3, how do you obtain the matrix of transformation given the object and the image? So when you're revising, ensure you get to understand those 3 components so that you will be able to cover this part well. And so in this case now, we want to start with a very simple case. In this case, you are told to simply find the image. Find the image of 6, 9 under an enlargement, given by the matrix T 2, 1, 4, 3. Again, I mentioned something to do with the pre-multiplication. And so I will take you back to where we were. This is where we were when we were looking at pre-multiplication. And I mentioned something at this point. I said that Pre-multiplication is going to be mostly applied in this topic, because most of the things we are going to deal with will be matrices of 2 by 1. And for you to be able to get the compatibility of matrices, you must be able to know that the number of rows and the number of columns in matrix 1 and matrix 2 must be able to match for the matrices to be compatible. So if we are dealing with coordinates, coordinates are usually in the order of matrix 2 by 1. So we cannot do post-multiplication. We will be doing what we call pre-multiplication so that we can make those matrices compatible. If you do the post-multiplication, those matrices will never be multiplied if that happens. So ensure that when you are carrying out multiplication, in this case, you do what is called pre-multiplication. And pre-multiplication simply means take the matrix before the coordinate so that you can be able to obtain the image. So let's carry out the calculation of our example. This is where we are. So we'll take our matrix. We'll take our matrix, which is 2, 1, 4, 3, and multiply this one by 6, 9. Again, remember, we are doing multiplication of matrices, and so on the basis of row by column. 2 by 6 gives us 12. We add 1 by 9 gives us 9. Then 4 by 6 to give us 24. We add 3 by 9, 27. So it gives us our value 21. And then 24 plus 27, that should give us 51. And so in coordinate form, then it means our value becomes 21, 51. That is the coordinate of the point P. So if that happens, then we shall say the matrix has undergone simply an enlargement in that given that matrix. Again, on the same enlargement, I want you to remember something, that we have what we call the matrix M. Matrix M given by K, 0, 0. These are common matrix of enlargement. These are a matrix of enlargement with scale factor K and the center 0, 0. It is important to know that that is a common matrix, that for any matrix of enlargement where the scale factor is K and the center is 0, 0, then we have this kind of matrix represented by K0, 0, K. For example, if you find we have a matrix of this nature, 2, 0, 0, 2, then if you are describing this matrix, it's simply a matrix of enlargement, scale factor 2, and the center is 0, 0. If you have this matrix 1, 0, 0, 1, though this is an identity matrix, but in terms of enlargement, this becomes a matrix of enlargement, scale factor 1, center 0, 0. Again, you can have a case, for example, a third, 0, 0, a third. It still means the same. These are matrix of enlargement, scale factor 0, 0, and center 0, 0, and the scale factor is a third. So that is how we get the general matrices general matrices for enlargement. Number 2, let's look at our case number 2. We're told to find the coordinates. Find the coordinates of A prime, B prime, C prime, the image of ABC under a transformation T 1, 2, 1, 4. Given that A is 1, 1, B is 2, 3, and C is 4, negative 2. Find the coordinates of A prime, B prime, C prime, the image of ABC under transformation T 1, 2, 4, that is 1, 4, given that A is 1, 1, B is 2, 3, and C is 4, negative 2. So we have 3 points, but these 3 points, A, B, and C, are what we call the object points. So we are supposed to obtain the image points, which is A prime, B prime, C prime, under the transformation matrix T, which is 1, 2, 4, 1, 2, 1, 4. So we proceed as follows. We take our matrix 1, 2, 1, 4, and then we pre-multiply this matrix by the object points. So we have A, B, and C. You can put them together so that you multiply as 1. A is 1, 1. That is, now we put 1, 1. B is 2, 3. And C is 4, negative 2. 4, negative 2. So we follow the procedure, which is the row by column multiplication. We start with this row and this column. So 1 times 1 gives us 1, plus 1 times 1, that is gives us 2. So in total, let's write it as 3. That will be 3. Then 1 by 2 is 1. 2 by 3 is 6. When you add, that gives us 7. Then 1 by 4 is 4. 2 by negative 2, negative 4. That gives us 0. Then downward, now we have 1 by 1 is 1. 4 by 4 is 4. Total, that is 5. 1 by 2, that is 2. 4 by 3, that is 12. That gives us 14. And then we have 1 by 4 is 4. 4 by negative 2 is negative 8. That gives us negative 4. Negative 4. So now this becomes the coordinates of A prime, B prime, and C prime. Now in coordinate form, because we've been asked the coordinates, we put it horizontally. We have A 3, 5, B prime 7, 14, and C prime 0, negative 4. This becomes the coordinates of A prime, B prime, C prime. So again, that takes us to the first part. The first part was, how do you obtain the image given the object and the matrix? So that is our first note. You should have noted that is given the object, and the matrix, of transformation to obtain the image, then you do pre-multiplication. You pre-multiply the matrix, that is the object points by the matrix, And we're still emphasizing that here you must ensure it is pre-multiplication, because if you do post, like if I decide to start with this 1, 1, and then the matrix comes next, then that matrix will be incompatible. That is part 1 of our discussion on this topic, that we obtain the image by looking at the matrix of transformation and the object, and then we do the pre-multiplication to get the image. Number 2, it is now captured in our example number 2. Our question now will be, that should be our question number 3. We are told to determine the matrix of transformation the matrix of transformation A, B, C, D that maps A 1, 2 and B 3, 5 onto A prime onto A prime 5, 3 and B prime we have 2, 6. Now this is now when you are given the matrix, you are given the object and the image. How do you obtain now the matrix of transformation? Again, dear students, what you need to do, remember the procedure we've highlighted before is pre-multiplication of the matrix. So if I take the matrix A, B, C, and D, and I multiply this one by A, which is 1, 2, and B, which is 3, 5. This is A, B. I should be able to get A prime and B prime. And in this case, our A prime is 5, 3, and B prime is 2, 6. So we are going to obtain pairs of a simultaneous linear equation. And how will that happen? We multiply A by 1, that gives us A, plus B by 2, 2B. And so that gives us the result of 5. So this should be equal to 5. I take again A by 3, 3A, plus B by 5, 5B, to give us, on this side we have 2. So that is our equation 1 and equation 2, which have the same components. So we can be able to eliminate A or B. So by elimination, then we will be able to work out this one. We have 3 and 1 if I'm eliminating A. So I'll have 3 by A, that is 3A, plus 3 by 2B gives us 6B, is equals to 3 by 5, that is 15. 1 by 3A, that is 3A, plus 1 by 5B, 5B, and that gives us 2. We subtract these 2, so we have 0 with B is equals to 15 minus 2, 13. Then once we have that as 13, we take one of the equation, either 1 or 2, and so we can say A plus 2B is equals to 5. Replace B with 13. So we have A plus 2 into 13 is equals to 5. 2 times 13, that is 26. Crossing the other side, it means A is equals to 5 minus 26, which is negative 20, 21. That is our solution for A and B. Again, we go to the second case now. C times 1, that gives us C, plus C times 2, C times 1 is C, then D times 2, 2D. This should be 2D is equals to 3. Again, C times 3, 3C, plus 5D should be equal to, that is 6. Again, we eliminate C because we have C here, it is 1. I put 3, then I put 1 on this side. So that I have now 3C plus 6D is equals to 9. Again, this side, 3C plus 5D is equals to 6. Good. So let's subtract this. 6D minus 5D, that gives us D, is equals to 9 minus 6, 3. So if that is the case, then one of the equation, A plus 2D, sorry, that is C plus 2D, 2D. We have, this is C. C plus, that is C plus 2D is equals to 3. So we replace in for D, meaning our C will be equal to 6, that is negative 3. And so the matrix A, B, C, D will now be given by A. A is negative 21, B 13, C is negative 3, and then D is negative 3. That is 3. Good. Yes, that is how we obtain the inverse. It is as simple as that. Again, students, you should have noted all this relies on the first part. The first note is pre-multiply the matrix of transformation by the object point to get the image. Then in this case, when you are working out to get the matrix, definitely we are going to obtain what we call a pair of simultaneous equation, which we will solve using either elimination, substitution, or we can even use a matrix method. Now, that is part 2. What about part 3? But even before we mention about part 3, know that in some cases, you'll be given a question that is an object, a plain figure. For example, a rectangle. You're told a rectangle A, B, C, and D has these coordinates, A, B, and C. Then you're given the coordinates of A prime, B prime, C prime, and D prime. It does not matter. What you simply have to do is take at least 2 object points and their images. So if you are given 4, only 2 will be important to you to help you get what you call the simultaneous linear equation. So you will not use all of them. Just take 2 and their images. Then you'll be able to get the equations to solve. So in the next part, this is our question number 3. In our next part now, we want to look at a case whereby you've been given now the image, and then you're told to get the object. So this is the question. That is our question 4. Determine the coordinates of P and Q mapped onto P prime 3, 5 and Q prime 1, 2 by a transformation matrix, by transformation matrix T 1, 0, negative 2, 1. So that is now our question, which will give us the analysis of our third part of this topic. When you're given the image and the matrix, how do you get the object? Because we've been doing given the object and the matrix. All this, the foundation is still based on the part of pre-multiplication of the matrix of transformation and the object point. So if I take now my matrix, which is 1, 0, negative 2, 1, we multiply this one by P and Q, and let's give our P the coordinates AB and give this one XY. Should give us the image, which is 3, 5, and then we have 1, 2. So this is our P prime, Q prime. So what we do, we multiply again 1 by A is equals to, because if you take 0 by B, it will be 0. So we equate this one to 3. It means our A is now already found to be 3. Again, if I take 1 by X, that will be 1X. 0 by Y, it will be 0. So our X is 1. Negative 2 by A, negative 2A, plus 1 by B is B, should be equal to 5. But remember, our A is 3. So replace here 3. Negative 2 into 3 plus B is equals to 5. This will imply that B is equals to 11. Then take again negative 2 by x, negative 2x, plus 1 by 1, that is y, is equals to 2. Remember, our x is 1. So replace here with 1, minus 2 into 1, plus y is equals to 2. Therefore, our y is equals to what? 4. And so we write now the coordinates p becomes p tulipatia x, a and b. So now inakuwa a is 3 and b is 11. Again, q tulipea, that is x and y. Now we have 1 and then 4. Those are the coordinates of the object p and q. So students, that is our analysis of matrices and transformation, the first 3 parts, which about getting the object, image, and the matrix. In the second case now, when we are looking at now transformations, we can be told to describe a transformation, but before we describe the transformation, we have to go back and see something we call the similarities of objects and the image. And so that is now our next item. Our next item, we're talking about area scale factor. Area scale factor. That is ASF. Now, we can have a case for the object and the object being mapped onto an image with a certain area. So in this case, we have to connect between the object area and the image area. Remember, in your form 2, area scale factor was given by the image area, or the area of the image, over the object area. That is the relation that we used in form 2 under similarities and enlargement. And we again said that this ratio is related to what we call the linear scale factor. And to say the linear scale factor squared gives us the area scale factor. So those are the foundations that are covered in form 2 topic 8 when you're looking at similarities. So when we come now to form 4, we are not going to apply linear scale factor because this is not about similarities, but rather we are talking about matrices. So we are going to be given the object area and the image area, or the matrix of transformation. So in this case, if we have the matrix of transformation, given a matrix T, A, B, C, and D, A, B, C, and D, then the area scale factor is determinant of the matrix. When you get the determinant of the matrix, it will be equal to the area scale factor, which is the image area over object area. So we look at this case very keenly, because most of exam in paper 2 section 1, you'll be given a question on the area of the image and the area of the object connected with a matrix of transformation. So we are saying for you to get the area scale factor, then you simply take the determinant of the matrix. And that determinant of the matrix, or the area scale factor, should be the image area over the object area. So let's see practically using a question or an example for this part. A question? A question? So we can have our question. You are told to okay, we have our question. So let's look at an example of our question. You are told to determine the, simply determine the area area of triangle ABC, which is mapped onto A prime, B prime, C prime of area 30 centimeters squared by a matrix of transformation T at 3, 1, 4, 7. We need to determine the area of the triangle ABC, which is mapped onto A prime, B prime, C prime of area 30 centimeters squared by a matrix of transformation T 3, 1, 7, 4. That is the matrix of transformation, and that is the area of the image. So anytime you see this case, then remember one thing, that the area scale factor, remember the area scale factor is equals to the image area divided by the object area. And this is equal to the determinant of the matrix of transformation. So the first task that we have in this case is to obtain the determinant of this matrix. And we say the determinant is simply the product of element in the leading diagonal. We minus the product of elements in the other diagonal. So we will take 3 times 4. Then we minus 7 times 1. 3 times 4, that gives us 12. 7 times 1 gives us 7. And the difference is 5. So it means, therefore, the ratio, which is the area scale factor, is equal to 5 units. So we go back to our first relationship, this relationship. We are saying that the area scale factor, which is now equal to determinant, is the image area, which is given as 30, over the object area that we are looking for. So let's give it x, should be equal to the determinant, which is 5. So remember, any number is over 1, and then we do the cross multiplication to have 5x is equals to 30. So how do you get x? Divide by 5 on both sides, and so it means x is equals to 6. And what is x? X is the area of the object, meaning 6 centimeters squared. So that is the area of the object, and that's how we calculate the area given the matrix of transformation and the object area. Again, it can happen the other way. You can be given now the object area and the matrix of transformation. Do the same application. Know that when you have the area scale factor is the area of the image divided by the area of the object, and should be equal to the determinant of the 2 by 2 matrix. So that is the fourth part of this topic. We can do one last example. You are told to, number 2, given that an object of area 75 centimeters squared is mapped onto an image of area m centimeters squared by a matrix -1, 7, 2, 4. Determine the value of m. So in this case, we've been given the object area which is 75 centimeters squared, being mapped onto an area of the image, that is m centimeters squared, by a matrix of transformation, negative 1, 7, 2, 4. So when you're given this case, then we need to know what we've said before, is that the area scale factor is equals to the image area over the object area, and that should be equal to the determinant. And so how do we get the determinant? Our determinant will be equal to, we take the product of elements in the leading diagonal, that is negative 1 times 4, then we minus 2 times 7, so that will give us negative 4 minus, this case we have 14, and so when you subtract this, you should get negative 18 as our determinant. So we come to our working now, the image area, which is not known. So we take 75 over, now we have the object area, which is the image area, which is m, should be equal to negative 18. And so in this case, it's over 1. We cross multiply, we'll have 18m, that is negative 18m is equals to 75. But remember, we take the absolute value of m because we're talking about area, and area cannot be a negative value. So we take the absolute m. So it will be 18m is equals to 75 divided by 18 divided by 18. So 75 divided by 18 from your calculators, 75 divided by 18, that should give us 4.17. That is 4.167 to 4 significant figures. And so this becomes the value for m. And remember, it is in centimeters squared. Yes, now let's see the response from students and see how we can be able to help them. Now there is one. We have one from Millie from Misesi. Millie from Misesi is asking. We determine the matrix of transformation that represents the following transformation, that is reflection x plus y is equals to 0, followed by a positive quarter turn about 0, 0. So now in this case, we have a transformation, and the transformation that we are dealing with is a transformation which is a reflection in the line x plus y is equals to 0. If you work out, this line is the line we are talking about, y is equals to negative x. And I say that this line has what we call a negative slope. It has a negative slope of 1. Or simply the gradient is equals to negative 1. That's what it means by this case. So if we carry out this reflection on that line, it is then followed by what we have, that is a positive quarter turn. Now talk about the positive quarter turn. The positive quarter turn, that is about the origin 0, 0. It means we rotate this. This is a rotation of 90 degrees, plus 90 degrees about the point 0, 0, or the origin. So if you have this kind, then in rotation, we have this. If this is a rotation, it employs this relation that R alpha, meaning R is for rotation, should be in the form of cos alpha, negative sine alpha, then we have sine 180 degrees, then cos 180 degrees. And so alpha, in this case, that is, sorry, not 180, but 90, because we're talking about 90. So it will remain to be our alpha, but now our alpha here will be given by 90 degrees. So we want to choose a point. Let's try to choose a point and have a point, for example, a point 2.5. Now the point 2.5 can be reflected on this line y is equals to negative x, which gives us a negative slope of negative 1. And then you should remember that the angle of rotation, the angle that is made by the line, if we have, this is the line on the x-axis, if this is the angle theta, then the gradient is always equal to, tan of the angle theta. If this is the x-axis, the line makes, or the angle the line makes the x-axis is supposed to be, the tan of that angle should be equal to the gradient. So if now we have the point 2,3 in our case, let's see practically how it will behave. So this is our x, this is our x, this is our y, x, then we have this is as our 0. Then we can be able to have 1, 2, negative, that is 1, 2, 3, 1, 2, 3, 1, 2, negative 1, negative 2, negative 1, negative 2. So the line y is equals to negative x, that should be this line. That is y is equals to negative x. So our point 2,3 will be somewhere here. That is 2,3. Let's use the point 1, 1, because that is more closer. 1, 1. And so if I have that as 1, 1, then I will be able to get the directly opposite, because it's a reflection. This will be the point now. If this is P, then this becomes P prime. P prime. Then this P prime is rotated through 90 degrees. 90 degrees about 0, 0 anti-clockwise. Then if you join this, practically joining this to the center, then we'll have 90 degrees. This is half. So 90 degrees will be back on the line. So we have the point which will be here. That will be the point P double prime. So we've moved from P to P prime, then P prime to P double prime. So the image will be the point negative 1, 1. So that will be our image. Again, someone has also asked about, we repeat the working on the coordinates under the transformation. Please repeat the working on coordinates under transformations. So I think that is based on the same case. We are looking at the transformations and on the coordinate system. So what you simply have to know is that, for example, you'll be given a case A, which is 1, 1, B, 2, 3, and C, you are told this is 2, 5. And then you are given a matrix of transformation, the matrix M, which is 1, 4, 2, 6. So what you do, the procedure will be obtain the image. Obtain the image. You obtain the image. And how do you get the image? You pre-multiply the matrix M. That is 1, 4, 2, 6. And then 1, 1, 2, 3, 2, 5. then you have A prime, B prime, C prime. You get the image for A prime, B prime, C prime. Then once you obtain that, then you draw. You simply draw ABC, and A prime, B prime, C prime on the Cartesian plane. You draw it on the Cartesian plane. And so after you've drawn on the Cartesian plane, be able to compare and see whether the matrix M fits either as a reflection. Work it out and see if it's a reflection, if it's a rotation, if it is a rotation, if it's a translation. If it's not a translation, it will be an enlargement. If it is not an enlargement, then it will be a shear matrix. And lastly, it can be a stretch matrix. So those are the areas that you look at when you draw the triangles on the Cartesian plane. So that is briefly what we've seen. We have a student that is Boston. Boston is saying, help me out. When I'm given a scale factor, the image of P, which is 0,2, under an enlargement, the scale factor 3 is 4,6. Find the center of enlargement. So again, this is now a case for now scale factor, that is enlargement, and we are told that the point is, that is the image of P. P is 0,02. It gives us P prime, and P prime is 4,6, and the scale factor is 3. Our scale factor is 3. Again, this is now what you can draw. If you draw it, what will happen is that we have the X and the Y, the X and the Y axis. So we have 0, 1, 2, 3, 4. Let's have 5 and 6. So I have 1, 2, 3, 4, 5, 6. Then on the y-axis, 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6. So we have the point 0, 2, 0, 2, that is our point P. And then we have a point P prime, which is 4, 6. 4, 6 is somewhere here. This is where you have 4, 6, P prime. And then this is the point P. So we need to obtain the center. So how do you get the scale factor? The scale factor of enlargement is simply the image distance. The image distance we divide by the object distance. And in this case, the image distance, that is the distance from the object, the image from the distance from the image to the center. And so we have to set our center, and this is a positive scale factor. So if I join these two points, we now obtain our image. We obtain our center. When we join the two, we draw the perpendicular, a perpendicular bisect of this. So we'll have this, because when you take the object joined to the image, then you draw the perpendicular bisector. You draw the perpendicular bisector. The perpendicular bisector lines will meet at the center. Meet at the center of the two. And so in this case, we have only 2 points. That is the point P and P prime. So if we join this and draw the perpendicular bisector, we only have one line. Now, this distance has to be equal to 3 units, the image distance over the object distance. So it tells you that in this case, for us to be able to obtain the image distance and the object, means the center should be away from the object and the image. And so it should be this number of units, and these units are on the x-axis. If you look this on the x-axis, these are 4 units. So if we produce this line, now we'll have 4 units. From the center, we expect to add 2 units. So we have, this is, I hope you'll be using the scale, the scale, and so you can be able to get the exact point using 2 units from the Cartesian plane. And so we'll have, this is somewhere here. So that now we have from this point to this point to give us 6 units. And then if we have from this to this, then we should have, to get 3, we need to have this to this to get 2 units. So now at this point is the point -1, -2. So that now this is our center. And in our center now will be 0, that is -2, 0. So that from this point to the point P prime, which is now 4, 6, to the point 4, 6, it will give us 6 units, which then gives us this relation that 6 units now divided by, if you divide this by 2, it should give us 3, which is the scale factor. And so that's why we now need to look at the difference between these two. It is simply 6 units, then divide it by 2, you'll get the scale factor, which is 3. So those are questions that are mostly for Form 2 work. But we shall look at more, you can practice more on the ones applying now matrices, so that now when you're given the point P and there is a matrix, then you can be able to formulate the scale factor. But for the general case, we have a general case for enlargement. If the center has been specified to be 0, 0, and then the scale factor given as K, then we said it is of the general form K, 0, 0, K. And so in this case, if it was to be the center 0, 0 and the scale factor is 3, then this could have been our matrix 3, 0, 0, 3. So I think those are what we have from our viewers. I want to thank you for following the program and being part of the lesson, and for being attentive and going through each and every component we've looked at. From that point, we can end our lesson for now. We'll meet next time when we shall do more of matrices and transformation. Remember, we've not drawn questions involving transformation, so you can practice on them. When we meet next time, we shall be able to draw them and be able to see how we work it out on the Cartesian plane. I've been your teacher, Mr. Elfas Ndenga. I wish you a nice day, and keep revising and practicing even as you stay at home. Enjoy your day.
Do you love